Hi everyone, I'm Bang Dang Fam. Today I'll present BluRef, unsupervised image deblurring with dense matching references. This work was done while I was at Qualcomm AI Research. Let's discuss the motivation starting with the current standard, supervised deblurring method. For training, you need paired data, each blurry image paired with its exact sharp counterpart. As you can see at the bottom, this comes with three problems. It requires paired data, a bulky capture setup with beam splitters and synchronized dual cameras, and it underperforms on unseen blur types, actually. So what about unsupervised methods? They don't need paired data, and that's a real advantage. We simply collect blurry images and sharp images separately. No complex setup needed, but here's the catch. During training, these methods form pairs by randomly picking one blurry image and one sharp image, and the paired images don't share any content. Notice the blur and sharp have totally different content. The model only cares about the blur versus sharp domain difference. This is content-agnostic pairing. And the consequence? Poor reconstruction quality, so we remove the need for paired data but sacrifice reconstruction quality. Now, here's our key observation. Within this pool of sharp images, there are frames that actually share similar content with the blurry input, which are captured from nearby viewpoints or different times. What if we could leverage these reference frames while still remaining fully unsupervised? And this is the BluRef's motivation. As you can see, we connect the blurry input to sharp references that share similar content, and this is the first truly reference-based unsupervised framework. BluRef uses dense matching to find pixel-level correspondences between the blur and these references. Unlike prior methods, our pairing is content-aware, shown here by the green arrows linking to references with similar scene content. And importantly, sharp references are only needed during training. At test time, BluRef performs direct deblurring, following the same inference procedure as a standard single image deblurring network. One blurry input in, one sharp output out, no references, no multi-stage pipeline. So what you deploy is just a lightweight deblurring model, same computational cost as any supervised backbone. Here are the headline numbers. On real-world blur from RMB2V, BluRef achieves 27.87 dB, surpassing the supervised upper bound of 27.43. On PhoneCraft, a fully unpaired smartphone dataset, we achieve the best NIQE and FID scores among all unsupervised methods, and all of this with zero paired training images. So how does BluRef work? Stage 1, we collect a blurry image and n unpaired sharp references from similar scenes. These don't need to be aligned. They can come from different viewpoints and different times. We feed them into a dense matching module G. Stage 2, the dense matching module finds pixel-level correspondences between the blur and the references, producing a pseudo-sharp image and a confidence mask. The confidence mask tells us which regions have reliable matches and which don't. Importantly, G is self-supervised, trained only on sharp images with synthetic warps, so no blur domain data leaks in. Stage 3, we train a deblurring backbone using the pseudo-sharp image as ground truth, weighted by the confidence mask. But there's a problem. If we only generate the pseudo-ground truth once, the quality is low early on when the dense matching struggles with heavily blurred inputs. The model can never improve beyond that initial ceiling. This is where iterative refinement comes in, the core of BluRef. After each training epoch, we take the improved deblurred output and feed it back into the dense matching module to regenerate a better pseudo-ground truth. Better deblurred image means better matching, which means better pseudo-ground truth, which means a better model. This virtuous cycle continues throughout training. And crucially, no iteration is needed at test time. Okay, now it's the results. As described at the top, we compare BluRef against existing unsupervised methods and supervised upper bounds across GoPro and RMB2V. Just looking at the table, unsupervised baselines sit in the low 20 seconds. BluRef with NAFnet progressive averaging reaches 31.94 on GoPro, just 1.4 dB below supervised NAFnet at 33.32. On RMB2V, we hit 27.87, actually surpassing the supervised Restormer at 27.43. Also notice, when delta increases from 1 to 20 frames, meaning references are much further from the blurry input, performance drops only marginally. This shows BluRef is robust to temporal misalignment. For the qualitative results, looking left to right, the blur input, then dual-GAN, UID-GAN, UA-UD, all still heavily blurred. Our results with Restormer and NAFnet backbones recover much cleaner details, closely matching the ground truth on the right. Finally, on PhoneCraft, a challenging real-world smartphone dataset with no paired ground truth, BluRef produces visually cleaner results than blur to blur and BSR-GAN. And when combined with blur to blur, we get the best scores across the board, NIQE of 8.47 and FID of 5.62. This shows that BluRef is complementary to existing domain adaptation methods and highly practical for real deployment scenarios. To summarize, BluRef eliminates paired training data by leveraging dense matching with unpaired references, achieving near-supervised quality in a fully unsupervised setting. Thank you. Happy to take questions.